Hi everyone, my name is Maddie Andres, and today I'll be teaching you about math and the science of sound and how they relate to each other. Let's start at the beginning, defining sound. Sound, simply defined, is interruptions in the flow of air, although sound can travel through anything that compresses, such as solids and liquids as well. Sound waves travel away from the source of interruption, like rippling waves in the water. In this picture that I have attached, you can see the initial point where this sound is coming from right here in the center of all these circles. And then you can see all the ripples going out from that initial point of quote-unquote interruption, as we say with sound. And so what is happening there, why there's all these little dots, is because that represents the molecules in the air. When you sing, it disrupts the molecules in the air and displaces them, and then they return and then displace again. But in this process of displacing and then returning, you have the rise and fall of what we would call a sound wave. Now, the amount of airflow interruptions per second is called pitch. A low pitch is considered to have less frequent interruptions per second, and a high pitch has more frequent interruptions per second. This phenomena is actually represented in what's called a sound graph, which is over here on the left in this picture. You can see with the low pitch, the wave is actually it's longer, it's smoother, and you can see the rise and the fall of the wave is actually, it's a lot more shallow of a wave, you would say. And with high pitch, you'll see that it's a lot more jagged. There's a lot more rising and falling happening much more frequently. Therefore, pitch is measured in terms of frequency because we want to know how frequently the displacement and return of air is happening. So how do we make sound? Well, there are 5 requirements for most sound. We need a power source, an oscillator, or something that vibrates, a resonator, transmitter, and a receiver. When it comes to the human voice, our power source is our ribs, diaphragm, and abdominal muscles. And then from that initial source of power, it then travels up to our vocal folds, or cords, and those vibrate together very rapidly. Then that travels up through our vocal tract, and then resonates in these things called resonation chambers in our skull. And then, as this happens, we release the sound out into the air, and it gets transmitted, and then it is received by our ears and brain. And this process is actually very quick. By the time that sound reaches your ear, your brain interprets it in literally 0.05 of a second. As I mentioned earlier, when a note is sung, your vocal folds or cords vibrate up or down, creating different pitches. Although vocal ranges differ from one person to the next, the vocal range is best represented by the keys on a piano, which is pictured left, because all 88 keys represent the human capability for sound. Now, not everyone is going to be able to hit the lowest note on the piano or the highest note on the piano, but once again, it represents the capability of the human voice. And this is best represented by the piano. And so here in this picture to the left, we see this person is singing, and you can see where the vocal cords seem to be kind of pinching together at the top a little bit. And this is where we can assume that this person is singing at this higher level in their voice. And so because the vocal cords are striking together rapidly at this high point, we can assume that they're probably singing a high pitch, which is being compared to one of the higher pitches on a piano. So now that we have defined what pitch and frequency are in relation to sound, we can now calculate it without actually hearing a note at all. And this is possible through the equation Fn equals F0 times a to the n, where Fn equals the frequency of the note n half steps away, F0 equals the frequency of one fixed note that must be defined, a equals 2 to the 1/12th power, and n equals the number of half steps away from F0 the note will be. Here we have a limited version of the most common data table that is used to calculate pitch. This table uses A4 as its F0 or its fixed note, and so when A4 is played or sung, it vibrates at a frequency of 440 Hertz. So because we're making this value home or a fixed note, a note that has a higher frequency will have a positive n value. And here we have this represented with n equals 17. The note D6 is 17 half steps away from A4, and it vibrates at a higher frequency, we see. And so this means that n is going to be positive because the frequency is higher than the frequency of A4. Then conversely, if the frequency is lower than A4, N is going to be negative. So here we have an example of N equals negative 43 in D1. D1 is 43 half steps behind A4, and it has a lower frequency than A4, so therefore it is negative. Let's work through an example together. Solve using the following equation: Fn equals F0 times A to the n, given A4 is our fixed note and n equals negative 4. So given that A4 is going to be our fixed note, we're going to return to this table again, and we find that A4 vibrates at a frequency of 440 Hz. I would like to remind you before we start solving, once again, that Fn equals the frequency of the note n half steps away, F0 equals the frequency of one fixed note that must be defined, A equals 2 to the 1/12th power, which it always will be, and n equals the number of half steps away from F0 the note will be. Returning to our equation, we're going to substitute in for F0 440 because we know that the given note A4 vibrates at a frequency of 440 Hz. Then we're going to substitute in 2 to the 1/12th power for A because we know this is a constant value, and then the negative 4th value in for n. So beginning to solve, we're going to use the order of operations, so we're going to start with the exponents. So we take 2 to the 1/12th power and then put it to the negative 4th power to find that it equals 0.793700526, which then multiplied by 440 will equal 349.2282314. Rounding to the nearest hundredth, we will find that equals 349.23 Hz. Now I know it may seem like our work is done here, but we actually do have one more step, considering that we've only figured out the actual frequency that this note is vibrating at and not what the actual note is. And so we return to our table, we've tracked down the frequency 349.23 Hz, and we find it associated with the note F4. Therefore, the note negative 4 half steps away from A4 is F4. Now that we've mastered calculating pitch and frequency together, I would also like to show you how to calculate wavelength, as it directly relates to the answer that we found in our previous equation. And so wavelength is the distance between the peaks of each sound wave. It is represented by the equation Wn equals c divided by Fn, where c equals the speed of sound, Fn equals the frequency of the note n half steps away from the fixed note, and Wn equals the wavelength in meters. For the sake of this equation, we're just going to say that c equals the speed of sound at room temperature, which is going to be 345 meters per second. So then bringing it back to the equation, we're going to substitute in for c, 345 meters per second, and for Fn, we're going to take the value that we found in our previous equation for the frequency of the note F4, which we found was 349.23 Hz. So then dividing 345 by 349.23, we find that the answer is 0.98788876385, which we're then going to round to the nearest hundredth to find that it's about 0.99 meters. Therefore, the peaks of each sound wave in the note F4 are 0.99 meters apart. Alright guys, well that makes for the conclusion of this presentation. I just appreciate you so much for listening to this entire ordeal. I hope that it was half as interesting for you as it was for me. And if you have any questions at all, please just get a hold of me either in the comments section below or via Canvas, and I hope you enjoy this lame pun.